Welcome back. Let's dive right into this explainer. Today, we're going to trace this absolutely fascinating problem-solving journey of how AI learned to truly understand both text and images. If you've ever found yourself wondering how these models managed to cross the chasm from just parsing text to actually, seeing the visual world around us, well, you are definitely in the right place.
Because really, how does AI know what's in a picture? That's the ultimate question we're tackling today. We're talking about moving from a model that only understands words, just text on a screen, to one that can actually narrate the visual world. I mean, think about what a massive leap that is. For the longest time, an image was literally just a grid of meaningless pixels to a computer. But today, we're going to see exactly how researchers completely smash that barrier.
So, here is our roadmap for this explainer. Number 1, a quick transformers review. 2, we'll dive into vision transformers. 3, we'll check out CLIP. And 4, we'll wrap up with blip. Let's get into it.
Starting off with Section 1, Transformers Review. Okay, so to really understand how AI sees, we first have to recap how it reads. What we're looking at here is the scaled dot-product attention architecture. Basically, you're looking at exactly how an AI learns context. Every single token, or word, in a sequence attends to every other word. It computes similarities to highlight those key contextual relationships, and it does this regardless of how far apart those words are in a sentence. The huge takeaway here? The model understands the dependencies of the entire sentence all at once, rather than just reading it left to right like we do.
To make sense of that math, honestly, just think of it like a cocktail party. The query, or Q, is what you're looking for. Like, hey, I need to find someone who knows about AI. The key, or K, is the name tag on the people in the room broadcasting who they are. Hi, I'm an AI researcher. And then the value, V, is the actual content of the conversation you have with them once you match your query to their key. The model calculates a similarity score between queries and keys, uses a softmax function to turn those into probabilities, and then creates a weighted sum with the values. It's just a brilliant way to figure out exactly how much focus to place on every single word.
Let's zoom out to the macro view and see how this all builds into the full transformer architecture. We've got this two-part structure. Over on the left is the encoder, which processes the input sequence, let's say an English sentence, using that exact self-attention mechanism we just talked about. Then, on the right is the decoder, which generates the output sequence, like a French translation. But there's a really critical detail in the decoder, the masked multi-head attention block. That masking is absolutely vital. Why? Because it prevents the model from seeing into the future of the sequence it's trying to generate. It literally forces the AI to predict the next word based only on the words that came before it. Moving right along to Section 2, Vision Transformers. So, transformers absolutely conquered language, no doubt about it. But images are vastly more dense. If you try treating every single pixel like a word, the math just explodes. Now, for years, we relied on convolutional neural networks, or CNNs. These use local receptive fields to scan an image, kind of like looking at a scene through a paper towel tube. It's a very incremental focus. But vision transformers, or VITs, they bypass convolutional layers entirely. Instead, they chop the image into patches, treating each patch like a word. This completely solves that limitation of local focus. It gives the AI the ability to use global attention, meaning it analyzes the entire context of the image at the exact same time, capturing complex visual relationships right from the get-go. A real game changer. Which brings us to Section 3, Contrastive Language Image Pre-training, better known as CLIP. Okay, so now our AI can process text, and it can process images. But the next massive hurdle? Getting them to actually talk to each other. And CLIP does this using something called batch-wise contrastive training. During training, the system is fed a massive batch of images paired with their text descriptions. Then, this contrastive loss function kicks in, and it acts almost like a gravitational pull. It pulls the mathematical representations, the embeddings, of an image and its correct text close together in a shared latent space. At the same time, it shoves incorrect pairs far apart. Essentially, we are building this shared brain where the visual concept of a dog and the written word dog live in the exact same spot. And the ultimate result of all this gravitational pulling and pushing? Zero-shot learning. Because CLIP was trained on such a massive, diverse batch using this contrastive training, it developed an incredibly broad understanding of the world. And thanks to this, the AI can recognize objects, concepts, and even artistic styles in the real world that no human ever explicitly trained it to see. You don't have to train a new model to recognize a car. CLIP already understands the concept of a car from its vast pre-training, and it can identify it on the fly. It's honestly mind-blowing.
Finally, we arrive at Section 4, Bootstrapping Language Image Pre-training, or BLIP.
Now, as amazing as CLIP is, it does have a pretty rigid limitation. It can only match existing images to existing text. If you ask Flip to write a brand new, original sentence describing an image, it just can't do it. But Blip solves this lack of generation. Blip is entirely flexible. It extends way beyond just aligning things. It actually integrates them using a multimodal encoder-decoder framework. What this means is it doesn't just match a photo of a dog to the word dog. It can actually narrate, caption, and converse about the image. It understands deep context and narrative details. It can look at a photo and say a golden retriever is catching a red frisbee in a sunny park. That is a massive leap forward.
And to make the AI even smarter for our very messy real-world world, Blip uses a really clever trick: bootstrapping with noisy data. Look, real-world data isn't perfect, right? A lot of times, an image on the internet has a caption that barely makes sense, or it's only weakly aligned with the picture. But by deliberately including these imperfect, noisy image-text pairs in its training, Blip is actually forced to work harder to find the underlying connections. And surprisingly, this improves its generalization. It makes the model far more robust and adaptable when you hand it some weird or obscure image out in the wild.
But of course, the innovation didn't stop there. Enter Blip 2. The brilliant upgrade with Blip 2 is all about efficiency. It actually processes the image and the text in entirely separate pathways first. It only combines their information into a shared space later in the process. And because it doesn't have to fully integrate everything immediately right from the start, it is incredibly fast. This separate pathway approach allows Blip 2 to handle massive, large-scale datasets much more cost-effectively. It completely dominates zero-shot learning tasks without breaking the computing budget.
So wrapping up, it is just an incredible evolution. We've gone from models that basically just string words together, to vision transformers that can take in global visual contexts, then to CLIP, which finally bridged the gap between text and sight, and finally to Blip, which allows for deep, rich visual conversations. The foundation is absolutely built. So as these multimodal models continue to merge vision and language perfectly, we really have to ask, when AI can finally see and describe the world as well as we can, what new realities are we going to build with it next? Thanks so much for joining me on this explainer, and keep exploring.